The James Webb Telescope stands out as the premier global observatory in the field of space science. Its mission is to investigate the enigmas surrounding both our own solar system and distant worlds orbiting remote stars, and to delve into the complex structures of our universe and the role we play in it. Tasked with uncovering the deepest secrets of our solar system and the distant galaxies beyond, it continues to redefine our perception of the universe and our place within it. Recently, scientists turned the telescope's powerful gaze toward a star system located approximately 120 light-years away from Earth. What they found has sent waves of excitement and intrigue through the scientific community. The telescope detected compelling evidence of carbon-based molecules in the atmosphere of a distant exoplanet, strongly suggesting it may be an ocean world, an extraordinary revelation that deepens the mystery surrounding potentially habitable planets beyond our solar system. The exoplanet in question is K2-18b, a celestial body that has already intrigued astronomers for years now. Well, this new discovery has only intensified interest in the planet, as it offers the tantalizing possibility of life-supporting conditions. K2-18b orbits a cool red dwarf star known as K2-18 in the constellation Leo and lies comfortably within its star's habitable zone, a region where conditions may permit the existence of liquid water. This super-Earth, about 8.6 times the mass of our own planet, occupies a unique category of exoplanets that fall between the size of Earth and Neptune, a planetary class that is conspicuously absent from our own solar system. That uniqueness alone makes K2-18b an object of considerable interest. But what truly sets it apart is the composition of its atmosphere. Using its unmatched infrared sensitivity, the James Webb Space Telescope has identified the presence of carbon compounds, specifically methane and carbon dioxide, within K2-18b's atmospheric envelope. This points to the possibility of a hydrogen-rich atmosphere overlaying a planet covered in oceans, a configuration that could support life or at least the kind of chemistry associated with it. This discovery builds upon earlier data obtained by NASA's Hubble Space Telescope, which first offered a glimpse into K2-18b's atmosphere and opened the door for more in-depth analysis. However, while Hubble laid the groundwork, it is Webb's cutting-edge spectrographic capabilities that have delivered the most detailed atmospheric reading of a habitable zone exoplanet to date. One of the most intriguing aspects of the new findings is the potential presence of dimethyl sulfide, DMS, a molecule that on Earth is predominantly produced by marine organisms, particularly phytoplankton. Although evidence of DMS in K2-18b's atmosphere remains tentative and unconfirmed, the very suggestion of a biosignature gas being detectable from such an incredible distance has electrified researchers across disciplines. If validated, it would mark an unprecedented leap forward in our search for extraterrestrial life. Yet scientists are understandably cautious. A researcher from a University of Cambridge pointed out that while the presence of carbon molecules and location within the habitable zone are promising indicators, they are not definitive proof of life. The planet's structure, likely featuring a high-pressure mantle of ice similar to Neptune, covered by a thin hydrogen-rich atmosphere, could still be inhospitable despite the potential presence of oceans. These extreme conditions might render any liquid water either inaccessible or unsuitable for life as we know it. Nevertheless, what remains undeniable is the technological triumph of detecting such complex atmospheric signatures. The method used hinges on a phenomenon known as planetary transit, where a planet crosses in front of its host star from our viewpoint, causing a slight dip in observed brightness. During these transits, some of the starlight passes through the exoplanet's atmosphere before reaching us. This starlight carries with it valuable information about the atmospheric composition, as different molecules absorb specific wavelengths of light. Webb's instruments can capture and analyze these subtle changes with remarkable precision, offering insights that were previously impossible to obtain. Future observations using Webb's mid-infrared spectrograph are expected to further refine our understanding of K2-18b's atmosphere and climate and possibly confirm the presence of molecules like dimethyl sulfide. The ultimate objective of these ongoing studies is nothing short of revolutionary: to determine whether habitable exoplanets exist and, if so, whether they show signs of life. But the telescope's revelations are not limited to nearby exoplanets. In another groundbreaking observation, astronomers using Webb detected complex organic molecules, specifically aromatic hydrocarbons, in a distant galaxy formed when the universe was only about 10% of its current age. These molecules, which on Earth are associated with petroleum, coal deposits, and pollution like smog, were previously thought to be far too complex to exist so early in the universe's history. Their detection fundamentally challenges prevailing cosmological models by suggesting that organic chemical complexity arose much earlier than we once believed. The molecules discovered are not simple compounds like water or carbon dioxide, but instead large molecular structures composed of dozens or even hundreds of atoms. These are among the most complex organic molecules ever observed in space, and their presence in such a young galaxy raises profound questions about the early universe's capacity to foster the building blocks of life. The light carrying the signature of these molecules began its journey less than 1.5 billion years after the Big Bang. A blink of an eye in cosmic terms considering the universe is estimated to be around 13.8 billion years old. That astronomers can now study this ancient light in such detail is a testament to Webb's extraordinary sensitivity and technological sophistication. Prior attempts to detect organic molecules in ancient galaxies could only establish their general presence, but the Webb telescope allows scientists to map where these molecules are located within their galactic environments. One particularly puzzling discovery is the non-uniform distribution of these molecules in a galaxy known as SPT 0418-47. The irregularity adds another layer of complexity, hinting at processes we do not yet fully understand. Even more astonishing is that this early galaxy appears to be as massive as our Milky Way and already harbors stars that have produced as much carbon and oxygen as those in our galaxy today, despite being only a tenth of its age. Such findings suggest that galaxy formation and chemical evolution may have proceeded far more rapidly in the early universe than previously thought. Taken together, the discoveries of carbon-based molecules on K2-18b and complex hydrocarbons in a primordial galaxy offer a dual perspective on life's potential origins, one grounded in the search for habitable planets in our cosmic neighborhood, the other looking deep into the past to understand how the essential ingredients for life emerged in the early universe. These breakthroughs not only enhance our knowledge, but also provoke new questions about how common life-bearing worlds might be and how quickly the universe became chemically enriched. The James Webb Space Telescope has fundamentally reshaped how we explore space. With each observation it sends back to Earth, it challenges scientists to reconsider long-held assumptions and entertains the possibility that life, at least the ingredients for it, may be far more widespread than previously believed. The ability to detect subtle molecular signals from planets dozens or hundreds of light years away and from galaxies that existed nearly 13 billion years ago reflects an extraordinary leap in our technological capabilities. These advances are more than just academic achievements. They represent humanity's drive to understand the cosmos at its most fundamental levels. The discovery of carbon compounds in the atmosphere of K2-18b may not yet prove the existence of life, but it brings us closer than ever before to answering that age-old question: are we alone? Meanwhile, the detection of complex organic molecules in one of the earliest galaxies adds a new dimension to our understanding of cosmic history, suggesting that the chemistry of life was already underway when the universe was still in its infancy. As astronomers prepare for more in-depth studies and await further data from Webb's mid-infrared instruments, anticipation builds. The coming years may well see the telescope unveil more astonishing secrets that will continue to redefine not only our knowledge of the universe, but also our understanding of life's potential throughout the cosmos. With each new milestone, the James Webb Space Telescope affirms its role as a cornerstone of space science, pushing the boundaries of what we know and what we dare to imagine. It connects the distant past with the distant future, linking the chemical complexity of the early universe with the atmospheric mysteries of worlds yet unseen. In doing so, it extends an open invitation to continue exploring, questioning, and dreaming. As we gaze into the sky with Webb's eyes, we are not merely looking outward. we are also looking inward, confronting the fundamental truths of existence and our place in a cosmos far richer and more mysterious than we ever knew. This groundbreaking discovery made by the James Webb Space Telescope represents not just a leap forward in exoplanetary research, but also in our understanding of the early universe and the potential for life beyond Earth. As scientists continue to study K2-18b and similar sub-Neptune exoplanets, the line between known and unknown worlds begins to blur, allowing our imaginations and scientific pursuits to wander farther than ever before. The identification of carbon-bearing molecules such as methane and carbon dioxide in the atmosphere of K2-18b, combined with the absence of ammonia, adds a compelling chapter to the ongoing search for habitable environments beyond Earth. While the detection of dimethyl sulfide remains unconfirmed and tentative, its possible presence is nevertheless stirring excitement across the scientific landscape. On Earth, dimethyl sulfide is primarily a byproduct of biological activity, particularly by phytoplankton in the ocean. If this molecule is conclusively found in the atmosphere of K2-18b, it could mark a profound milestone, the first detection of a biosignature gas on an alien world. However, the scientific community remains rightly cautious. Interpreting chemical fingerprints in the atmosphere of distant planets is a complex endeavor, rife with variables and potential errors. Yet, even cautious optimism has fueled increased investment in further observations, particularly with Webb's mid-infrared instrument MIRI, which will be crucial for validating these early results and expanding our understanding of this mysterious exoplanet. K2-18b itself is an enigmatic world with a mass 8.6 times greater than Earth and a radius about 2.6 times larger. Its size places it in a category of planet not represented in our own solar system, larger than Earth but smaller than Neptune, adding to the difficulty of drawing comparisons. This unique classification, along with its potential hydrogen-rich atmosphere and hypothesized oceanic surface, makes K2-18b a prime candidate for astrobiological exploration. Orbiting a cool red dwarf star in the constellation Leo, the planet lies well within its star's habitable zone, the region around a star where temperatures might allow liquid water to exist. Despite this tantalizing setup, the precise conditions on K2-18b remain a mystery. Scientists speculate that even if oceans exist on the planet's surface, they could be under such high pressure due to the thick atmosphere and potential icy mantle that life, as we know it, may struggle to emerge or survive. Still, the excitement lies in the possibility that life doesn't have to resemble what we know on Earth. The very fact that these questions are now being asked with data in hand represents a significant step forward. With each new observation from JWST, our understanding of the diversity of planets in the universe deepens, and our criteria for what constitutes a habitable world continues to evolve. But the James Webb Space Telescope's revolutionary work doesn't stop with exoplanets. It has also made extraordinary breakthroughs in the realm of deep cosmic history. One of its most astonishing discoveries involves the identification of complex organic molecules, technically known as polycyclic aromatic hydrocarbons, in a galaxy formed when the universe was less than 1.5 billion years old. These large carbon-based structures are similar to those found in smoke and smog on Earth, in substances such as petroleum or coal. That they existed so soon after the Big Bang challenges long-standing assumptions about how quickly organic complexity could arise in the cosmos. Such molecules are not simple compounds. They consist of dozens or even hundreds of atoms arranged in intricate structures. Their presence implies that the basic ingredients for life may have been forming much earlier in cosmic history than previously believed. Prior to this, efforts to detect such molecules in ancient galaxies could only determine their general presence, not the specifics of where or how they were distributed within their host galaxies. Thanks to Webb's extraordinary sensitivity and resolution, astronomers can now pinpoint these molecules' locations and assess how their abundance and distribution evolved across different regions. The early galaxy in which these complex organic molecules were found, known as SPT 0418-47, has become a focal point of ongoing research. This galaxy was discovered to be surprisingly massive, already rivaling the Milky Way in size, even though it formed just a fraction of the time after the Big Bang. Its stars have already produced considerable amounts of carbon and oxygen, key elements necessary for life, which raises an important question. How did such chemical richness develop so quickly? The answer remains elusive, but the implications are profound. It suggests that the ingredients for life could have been present throughout much of the universe's history, not just in the more recent epochs as traditionally believed. This idea challenges and potentially reshapes our current cosmological models, pushing scientists to reconsider the timeline and processes that govern chemical evolution on a universal scale. The molecules observed in this galaxy are thought to be remnants of ancient stellar activity, created in the dying phases of massive stars and dispersed throughout interstellar space. Over time, these organic compounds may become part of molecular clouds, the cold, dense regions of space where new stars and planets are born. If such materials were present in significant quantities this early in the universe's evolution, then the seeds for life may have been sown throughout the cosmos far earlier than expected. Moreover, the distribution of these molecules in spt 0418-47 is not uniform, adding another layer of mystery.